Given our rational function, we want to determine all of the asymptotes of the function. So we're going to look at vertical, horizontal, and oblique asymptotes. This function cannot be reduced at all. The numerator cannot be factored, so we don't have to worry about canceling common factors and looking for wholes on this particular function. So let's start with vertical asymptotes. The way that we can find our vertical asymptotes is to look at the denominator of our function and find what values of x would cause that to be equal to 0. So if we take our denominator x minus 2, set that equal to 0, we find that x is equal to 2. So this function has one vertical asymptote with an equation x equals 2. So that's an equation of a vertical line. It's telling us an x value where this function is undefined. So next, let's think about horizontal. The way that we find horizontal asymptotes is to look at the degree of the numerator and the degree of the denominator of the polynomials that make up our rational function. So the numerator of this function, so we're looking at the largest exponent, is a degree of 2. The denominator has a degree of 1, because we could think of this as x to the first minus 2. So we want to compare these degrees. So what we notice is that the degree of the denominator is less than the degree of the numerator. So anytime the degree of the denominator is less than the degree of the numerator, our conclusion is that there is no horizontal asymptote. When this is the case, so only in the case where there is no horizontal asymptote, then we will also go on one additional step and look for what are called either oblique, or you can also call it a slant asymptote. So an oblique or a slant asymptote, as the name implies, is not a horizontal or a vertical line, but a slanted line. The way that we find this is that we perform polynomial long division or synthetic division to find the quotient of dividing negative 2x squared plus 7x plus 1 by x minus 2. So because of the format of my denominator being just x minus 2, I'm going to go ahead and use synthetic division to divide. So since it's an x minus 2, I'm going to put a positive 2 out in front and then take the coefficients from my numerator. So negative 2, 7, and 1. So in synthetic division, we just bring down the first coefficient, and then now we multiply and add and multiply and add. So 2 times negative 2 is negative 4. Adding 7 plus negative 4 is positive 3. Multiplying 2 times 3 is 6, and adding 1 plus 6 is 7. So in this particular case, we're going to just ignore the remainder. We don't use that at all. We are interested in the quotient. So the 3 represents the constant term. The negative 2 is the coefficient on our x term. So the equation of our oblique or slant asymptote, it's a line, y equals negative 2x plus 3 is our oblique asymptote. So this is a line that has a slope of negative 2 and a y-intercept of 3. So the graph is going to follow along this on its tails. Let's take a look at the graph with the original function and the asymptotes. So here's what we see if we graph this function. So the green line represents our vertical asymptote, x equals 2. The blue line represents our oblique asymptote, y equals negative 2x plus 3. And the red curve is our original function, g of x. So you can see how as the graph approaches the x value of 2, one side of the graph is going down to negative infinity and one side's going up to positive infinity. And as you go out to the left and the right side of the graphs, the tails of the graph or the long run behavior is following our oblique asymptote, y equals negative 2x plus 3. So the oblique or slant asymptote is telling us about the long run behavior, that the tails are not flattening out, but that they're following along this slanted line.